Hi guys, and welcome back. So in the last part here of chapter 2 of our lecture notes, we will classify, in a sense, all separable Hilbert spaces. So to be able to classify this, we need a new notion, and this is written here in the first definition. So working in two Hilbert spaces, H1 and H2. Notice here, by the way, I again use these subscript notations to indicate that these two inner products in general are not the same. Then we say that these Hilbert spaces are isomorphic. Well, if there exists a linear invertible map, a linear bijection U from H1 to H2, that preserves the inner product. That's what this equation means here. Okay, as such, an operator is called unitary, or some people call it a Hilbert space isomorphism. Later on, when we will discuss Banach spaces, there will also be Banach space isomorphisms. Okay, unitary, I think that terminology has become much more standard than Hilbert space isomorphism, so I will stick to that. Okay, so it's a linear bijection that satisfies this yellow box here, so that preserves the inner product. That's what it says. Okay, so this in mind, now we'll be able to prove this classification theorem here. So it says that a Hilbert space is separable if and only if it has a countable orthonormal basis S. What we already know, what we already proved, is one direction of this first statement, because this is a combination of that proposition right before the Gram-Schmidt theorem and the Gram-Schmidt procedure itself, right? You start with something separable, then you construct from it a linearly independent spanning set, and then you apply the Gram-Schmidt process, and what comes out is a countable orthonormal basis. And as it turns out, that is a two-way route. You can start with a countable orthonormal basis, and then the space has to be separable. That's probably easier to see than going the other route. I will write it down in a minute. Now, if the Hilbert space is then separable, so if you have a countable orthonormal basis, then there can only be two cases. If there are capital N finitely many elements in S, then H is isomorphic in the previous sense to the coordinate space Fn. So depending whether you're working here in a Hilbert space over the real or the complex number field, that F would either be, the real numbers or the complex numbers. In the notes, I think I formulate everything over the complex numbers. This was the convention I explained early on when we discussed this chapter. The second possibility, if there are countably many elements in S, then H is isomorphic to small L2, and that we already know is a separable space, of course. Okay, good. So now we will prove this result. It's fairly quick. Proof. So if, okay, let's write it down one more time. If H is separable, then it has a countable orthonormal basis by the previous two results. That was Gram-Schmidt procedure and that proposition right before it, by the previous two results. Okay, that I already explained. Now, conversely, if xj, j from 1 to n, is a countable complete orthonormal system for H, then the set, let's write it down, all linear combinations J1n alpha j xj, and now the alpha j's. Okay, so what I can do is there's two choices depending on the underlying field. It can either be alpha j rational or alpha j rational plus I rational. Okay, with n I will explain. Let me first write this down. Then this set, let's move it a bit to the left. This set I claim is, well, dense in H. Why is this? Well, because you start with a countable complete orthonormal system and you have the Fourier expansion theorem, right? In the Fourier expansion theorem, you expanded each vector in terms of the basis, right? That's precisely what you did. So then obviously you are dense in H because each one of these guys there, it converges to an element in the Hilbert space, right? So that is part of the Fourier expansion theorem. Okay. Moreover, this set is countable, and that is the reason why you do this little surgery here with your coefficients being either in the rational numbers or in rational plus I rational. Because the thing is, if your scalar field is let's write this in yellow maybe. If the scalar field is the real number field, you're going to go for the first option. If the scalar field is the complex number field, you're going to go for the second option, right? And remember, Q, the rational number, that is dense in R, but Q is countable, whereas R and of course the complex number field is not countable. That's why you do this, because you need something countable dense, right? That's what the theorem says up there. Okay, so since this set is countable, H is separable. Okay, good. So that now settles the first part. Hilbert space separable if and only if it has countable orthonormal basis. Now we will assume there's countable orthonormal basis, and then we will convince ourselves that there can only be two choices. Okay. Now pick an orthonormal basis. Say xj, j1n for h, and define, so I need to define this unitary map, right? Because the theorem says they are isomorphic. So they're not identical. It's just you can identify them, but they're not identical. Define U from H to L to N by, so here is the formula. So it maps U, takes an element and maps it, well, to the Fourier coefficient. And then you form a sequence out of all those Fourier coefficients, right? So, and the claim is that this defines a map from H to L2. And why is this guy here in L2? Well, you can now use two arguments, which are essentially the same. The simplest one is you just use Bessel's inequality. That's why a Bessel's inequality is so powerful, because the Bessel's inequality says that the sum over all, j from 1 up to capital N over the modulus, complex modulus squared of the xj's is at most the norm of x squared. So it's clearly finite, right? Or you can use Parseval relation. The Parseval relation is an improved version of Bessel's inequality because it gives you exactly the equality, because you're working here with an orthonormal basis, right? That's why. Okay, so this is well defined by either Bessel's inequality or Parseval relation. So this is this. If capital N is equal to infinity, then of course Ux is an element in L2N. So U maps into Cn if n is finite. Well, that's clear, because then your sequences, they truncate at some point, and then you have only finitely many elements up front, and that's precisely an element of the coordinate space. Maybe not Cn, this is what I write in the notes, but here I discuss this in general over Fn. If n is finite, or L2n if n is infinite. Okay, so that map is already goes in the right direction. Now we have to show that it satisfies that unitary character in the sense that it preserves the inner product. Okay, however, by the Fourier expansion theorem, or you can also use Parseval relation and the polarization identity, whichever you want, by the Fourier expansion theorem. So what can we say about x comma y? Well, look, so each one by Fourier expansion I can expand in terms of that basis xj, and this is a norm convergence sequence which converges independent of order, right? That's what we proved in the Fourier expansion theorem. So you do this for both entries, yx not j, k, y k, xk. Then of course comes the standard thing, you move the scalars out, one goes out as is, the other one comes out with a complex conjugate bar, and then what remains is the inner product xj with xk, but since these are orthonormal, again this collapses to just one value, and you can convince yourself what comes out here is x xj, and then y xj bar. Okay, so now here we should maybe use another subscript notation. So this inner product here, this is the inner product in L2, right? This is the inner product in L2, although I didn't use the specific nature of this. But that's what I start with. I start with two elements. Oh no, it's not in L2, it's in the Hilbert space. That's why I didn't use the specific nature. That's right, yeah. This is the inner product in the Hilbert space, these two guys. That's right. But now, what is this? Well, this is precisely ux, uy, and the product in, well, L2, or just a 2 inner product, right? Why is this? Well, because of the definition of the inner product in L2, right? The L2 inner product, maybe I shouldn't use x and y, okay, let's do it anyways, is just j1 infinity xj yj bar, right? That's what you have here. You should maybe identify this here with this, which is precisely the value of ux, right? That's precisely what's written up there. xxj, the jth entry of ux is the inner product x with xj, so that's precisely what's written here. So this you can write as u of x, if you want, the jth entry, like this. And then the other one, below the complex conjugate bar, is precisely, let's do it maybe dash dotted, is precisely uy and then the jth entry, right? And then you identify this quantity yj with this. And that's how you get it. This is equal to the inner product on L2 of ux and uy. Yeah, and that's precisely what you wanted to show, right? That this u preserves the inner product. ux, uy in inner product is precisely x, y in the other inner product on h. Okay? So that this is done, and now the only thing that I have to show is I have to show that it's a bijection, right? It's clearly linear. That map up here is linear. Because the inner product is linear in the first vector. That's why this thing is linear. So now I have linearity, I have the norm, the inner product preservation, and now what I have to show is that it's a bijection. So now you can easily see from the norm preservation that it's injective. You just take x is equal to y, you immediately conclude that u is injective, so then you have to check that it's also surjective. But here actually I will do better. I will write down the inverse right away, and then we will be done. Okay, so let's do this finally. U minus 1y j1n yj xj for any yn from n to infinity in L2 is a two-sided inverse to U. Okay, so let's check this. I need to check two equations. So I have to look at what does U do when I act on U minus 1y. Okay, so remember, U maps a vector in the Hilbert space to the sequence that is formed of the Fourier coefficients, right, with respect to those xj. So this will be a sequence, okay, and then I will have U minus 1y here, xj, j from 1 to n, right? That's, I think, how I wrote it up there. Yep, that's correct. Okay, so you have this, and now you use the formula. Maybe now when you plug it in, you should change the summation index from j to k, because j is already the running index in the sequence. So you do this, then you have k from 1 up to n, yk, xk, xj, j from 1 to n. And now you need to remember what are the vectors here, right? What are the vectors and what are the scalars and whatnot? Well, the thing is the this inner product here, right? So what you can do is you can move out this here and the sum. Those are the scalars with respect to this inner product, and then since the xk's form an orthonormal basis, that thing will, you know, collapse to just one element. So what you have here is precisely equal to, what was the outer running index? It was j. So it will be precisely byj, j from 1 to n. Yeah, but that's precisely the sequence y, right? So what you have shown is, sorry, I have to go back. You have shown that u minus 1y is precisely equal to y. So it is already a right-sided inverse. Now what we have to do is we have to show the other way. So we have to look at, say, now show u minus 1, say ux. Okay, so what goes on there? So u minus 1, that is simply j from 1 to n. And then ux, the jth entry of that thing, multiplied by xj, but the jth entry of ux is precisely the jth Fourier coefficient, right? You can just look at the definition of u. So this is xj. Yeah, but fantastic. This is precisely Fourier expansion theorem. That gives me that this is equal to x. Fourier expansion. Because remember, the xj's, they form an orthonormal basis after all. Yeah, well, and that's the second part, right? U minus 1 ux is equal to x. So it's indeed a two-sided inverse, and that's why you're done. Okay, in summary, U is indeed a bijection, and so altogether unitary. Okay, that's it. And that ends the proof of the theorem. Okay, excellent, very nice, very nice. So we have classified now to the end that in a separable Hilbert space, well, Benders can only be, you know, two options up to these, you know, isomorphisms, up to the Hilbert space isomorphisms. Then you are either working with coordinate space, finite dimensional, or you are in small L2, and that's it. Okay, good. So now, as I said, we will now close up for now the Hilbert space chapter, and we will start something else, so the Banach spaces. Historically, actually, and this is also a motivation why I do it this way, Hilbert spaces sort of came first. So quantum mechanics, this was born shortly after 1903, so more than 100 years ago, and then in the early 1920s, when quantum mechanics was invented, people started building the theory of functional analysis, and the first results, they were only formulated usually in Hilbert spaces. Then later, starting in the 1930s, so about 10 years later in the 1940s, then people realized that actually there's a sort of sea of results that you can prove without having the inner product. And that, brings us to a more general infinite dimensional space, and those will be the Banach spaces. Okay, so Banach spaces, they have very rich theory, although on the geometrical side they are far inferior to Hilbert spaces. Okay, so there won't be any inner products, we won't have any of these Fourier expansion theorems, or orthonormality doesn't make any sense in those spaces, but nevertheless there's really a remarkable ocean of results and applications out there that really need Banach spaces. So that's why we will spend now significant time on Banach spaces. Okay, so to begin with, we need to know what is a Banach space. Definition, or maybe I should write this here in blue, not in pink. So 3.1 definitions and examples. The Banach space chapter 3 is the longest chapter in the notes. So Hilbert space was rather short. Now Banach space is going to be much longer. So a Banach space named after Stefan Banach is a normed linear space X over, FR or FC, which is complete in the induced metric. Right, so remember, every normed linear space is a metric space, taking the canonical metric to be just a difference like this, and that's why you know what it means to be complete, because you know that notion for general metric spaces. Okay, that's the Banach space. Named after Banach. By the way, Hilbert, of course, Hilbert space is named after Hilbert. I never actually mentioned. Okay, so now what we will do is we will prove a series of examples, or assemble a series of examples in which we discuss, which spaces are Banach spaces. Okay, so the first one will be the sequence spaces. So small LP now for general P. In the Hilbert space section we were always in P equal to 2 because we needed the inner product. Now, as it turns out, with norms, P for 1 all the way up to infinity, they are all Banach spaces. Okay, so we proved a P equal 2 already, right? Because, for P equal 2 we showed it's a Hilbert space, so then it's in particular a Banach space. Now, as it turns out, using the Jordan-von Neumann theorem, the other values of P are not gonna give you a Hilbert space, okay? But they still give you a Banach space, and this is here the first example, okay? So how do you prove this? Well, as it turns out, if you revisit the example where I showed that small L2 is a Hilbert space, we looked at a Cauchy sequence, and then we looked at the coordinates of the sequence, formed a new sequence. This was this 3-step process. We found a limit candidate, then using Minkowski inequality showed that limit candidate is in L2, and then showed the convergence in the 2 norm. Now, as it happens, if you closely study that proof of completeness, then you realize it did not use at all the inner product. It only manipulated with the norms, with the 2 norms, and hence with Minkowski inequality. Yeah, but we proved Minkowski inequality for the general P norms on the P summable sequence spaces. So what I'm saying here right now is that proof that we gave back in the day for small L2 being complete, it lifts automatically to all these P's, Well, except for p equals infinity. Okay, so for p equals infinity, we'll have to give a separate proof. But for all the other p's, the proof that we gave back in the day for p equal 2 just generalizes. Okay, so I will write this down. Using the proof logic, you can check for yourself. So whenever in that proof you see something squared or a square root, now you just replace it by, well, pth power and 1 over pth root, right? Or pth root, rather. So using the proof logic behind the completeness, which is discussed, in the previous video and in the notes, of course, behind the completeness of L2n, we immediately conclude that LP is complete for all p's in between 1 but away from infinity, right? Because the difference with infinity is, as usual, you don't have sums that you operate with, but you have these suprema. So there you have to do something slightly different. It's complete for all p less than infinity. Okay? So what we do is, as I said, to see this, you just use the general Minkowski inequality for arbitrary p. And now what we will do is, in the next video early on, I will prove that also for p equals infinity, we are in a complete non-linear space, that is a Banach space. And after that, there come, let's count here, 1, 2, 3, 4, 5 examples, five more examples. So surely the next video, probably the next 2 videos, we will only spend discussing and proving certain normed-linear spaces being Banach spaces, or not being Banach spaces. There will also be examples where we show that they are not Banach spaces. Okay, so constructing Cauchy sequences that are not convergent in the space. Okay, then doing this, we will gain some first hands-on experience with Banach spaces, and then we will slowly start building Banach space theory, and then take it one video at a time. Okay, that's all. I hope I'll see you in the next video.